Once the analysis is complete, we understand whether the slopes are stable. If calculations show low safety margins or ground movement is detected, is considered reinforcement as the next step. However, expensive retaining walls or deep anchors may not always be necessary or even feasible. Often, simpler and most cost-effective solutions can significantly enhance slope stability. These measures don't rely on rare materials or complex technologies, but rather smart engineering decisions and, of course, available resources. So let's look at the approaches that offer a noticeable improvement in slope stability without major capital investment. Well, first, and often most effective measure is water control. As I mentioned earlier, water greatly reduces soil strength, so it must be kept away from slopes. Drainage measures can be very straightforward. For example, excavating ditches or channels to divert rain and meltwater from the slope crest, or installing drainage blankets or perforated pipes within the slope to reduce groundwater levels. And in open pit mines or waste dumps, the longitudinal ditches are often installed along berms to prevent erosion and saturation. Where possible, the water table is lowered by cutting a trench at the slope toe or by pumping water from wells. These methods are relatively inexpensive, especially when compared to the cost of full-scale slope collapse. Another approach is geometrical reshaping of the slope. This essentially means flattening the slope by redistributing material, and the most drastic method is to reduce the slope angle, cutting down from the top or adding fill at the bottom. While full regrading isn't possible, benches and berms can be added to break the height into smaller segments, shortening the potential slip surface and trapping falling debris. And even minor changes help. Relocating heavy equipment away from the slope crest or removing excess material from the top reduces driving forces. These earthwork-based solutions typically require only excavators or bulldozers, tools that are available on most sites and much cheaper than large engineering structures. So you can see on the video the process of determining the optimal pit slope angle using the combination of finite element method and the limit equilibrium method. The analysis begins with evaluating the stress distribution and identifying the geological and operational constraints. And based on these inputs, inverse approach is applied to calculate the slope angle that yields the highest factor of safety. The next step of measures focuses on surface protection and minor reinforcement to prevent soil loss, manage small slips, and slightly enhance soil stability. One cost-effective approach is simply slope vegetation. Planting grass or shrubs anchors the surface with roots, reducing soil erosion. And while it's not sufficient for deep-seated failures, vegetation effectively curbs the surface degradation. To aid plant establishment on steep slopes, biomats made of coconut fiber or synthetic mesh secure seeds and soil until roots take hold. And for tougher conditions, geosynthetics like geogrids or geotextiles are employed. Geogrids laid across the slope, filled with soil and gravel, create a mechanical interlock. And geotextiles act as reinforcement and separating layers, boosting slope resilience, particularly in fill slopes. So on rock slopes, options, of course, are limited, but wire mesh anchored to the surface is a common economical choice to prevent minor rock falls. And collectively, these surface techniques mitigate small-scale slopes issues that can lay the groundwork for more substantial solutions if required. And finally, let's consider localized reinforcement structures that can be relatively affordable. Gabions, for example, mesh box filled with rocks. It's a great example. They can be built into retaining walls at the slope toe. The rock can be sourced on site, for example, from waste rock, and the mesh is inexpensive, so result is a strong permeable structure that stabilizes and drains the slope. Another option is soil nails, slender steel bars driven or drilled into the slope at an angle, and they bond with soil resistant movement and are cheaper and easier to install than large anchors and piles. For temporary stabilization, even simple measures help. For example, covering the slope with plastic sheeting before heavy rainfall to prevent washouts. So individually, these methods may not solve large-scale problems, but together they can definitely meaningfully boost slope stability or buy time until permanent solutions are implemented.